In this lesson, we're going to look at how to determine oblique or slant asymptotes of rational functions. So occasionally, you're going to have a rational function that exhibits what's known as a slant or an oblique asymptote. So it would be that your blue function you see on your screen is approaching this red asymptote. And this wouldn't be just like a line like y equals 2 because it's not horizontal, it's on this diagonal. So that's going to be a linear equation, and we're going to determine how we determine the linear equation. So first of all, let's identify when this happens. And it happens in a rational function when the degree of the numerator is exactly 1 more than the degree of the denominator. And to determine this equation, what you have to do is you have to divide the numerator by the denominator using long or synthetic division. And remember, synthetic only works if you have a linear divisor in the form of x minus c. So the quotient polynomial is the equation of the slant asymptote, and you need to ignore the remainder. So let's, of course, illustrate this with an example. So we are told to determine any asymptotes and intercepts. So what I spot is, of course, that my numerator is exactly 1 more than the denominator in regards to the degree. So I know that there's going to be a slant asymptote. So I'm setting up my my long division. Synthetic's not an option here. And then I need a whole bunch of zeros as placeholders. So I check how many times does x squared go into 2x cubed, and it's going to go in 2x times. So I write this 2x directly above what it's like with, and then I multiply 2x times the divisor. So that's 2x cubed plus 2x squared minus 24x, and now I'm going to subtract, which is where I like to change my signs, and add. So this will give me negative 2x squared plus 24x. And I'm just going to bring down my plus 0 here. I'm checking now how many times does x squared go into negative 2x squared into negative 2x, and it goes in negative 2 times. So if I do negative 2 times the divisor, I get negative 2x squared minus 2x plus 24, and I subtract, produces 26x minus 24, but honestly I don't care about the remainder because this right here, if you notice, that's a linear equation. So I have a slant, or what's known as an oblique asymptote, and it is in the form of the equation y equals 2x minus 2. So it crosses, it has a y-intercept at 2, and then it has a slope of positive 2. So it's going to look something like this. And since the directions tell me to find all asymptotes, I recognize that there are also some vertical asymptotes, because if I factor this denominator, this would be x plus 4 and x minus 3. Nothing cancels, so there are no holes, but there are 2 vertical asymptotes giving me infinite discontinuity at x equals negative 4 and x equals positive 3. So I'm going to add those to my sketch. And x equals 3. I'm also told to graph the function and state the domain. I'm going to add my domain in. So this would be from negative infinity to negative 4, union negative 4 to 3, union 3 to infinity. So notice that the oblique asymptote does not break my domain, but it does affect my sketch. I just realized I skipped the x and y intercepts. So the x-intercept comes from numerator equal to 0. So this would produce x equals 0. So 0, 0 is going to be my x-intercept. And that's also going to be my y-intercept, because if I do f of 0, I will also get 0. Okay, so it's going to cross at the origin. Now, you can use your technology to help you create this sketch. And it goes oops, I just totally missed my origin. So it goes like this, and it approaches the vertical asymptotes. Notice it does cross over that slant asymptote there in the middle. But then it goes like this, and it gets closer and closer. I didn't really give myself adequate space. It's way up here for this part. I'm going to show you on Desmos now. So here is the function in Desmos, and the kind of cool thing is you can graph your asymptote that we discovered, the y equals 2x plus 2, or I mean to say minus 2. So that's the blue line that was just sketched by Desmos. There it is. And you can see there your function approaches that. Now your end behavior on the right would be that it's approaching positive infinity. It's not approaching that line, it's continuing to increase. And on the left, it's decreasing. Okay? Pretty cool stuff. Isn't math amazing? So we have one more here. And again, we're finding our asymptote. So immediately I see a vertical asymptote. I don't believe that numerator is going to factor. So vertical asymptote at x equals -4. I'm going to have infinite discontinuity. I do have a slant asymptote because the degree is exactly one more in the numerator than in the denominator. So I can do long division, or this would be a scenario because the divisor is linear. You could technically do synthetic using -4. So if you prefer long division, go for it. But this is where you pick off the coefficients of your trinomial. You put the value of the 0, which is -4, on the outside, bring down your 1, and then multiply, add. So 1 times -4 is -4, add, and I get -1. Back to multiplying by -4. This one's your multiplier. That's +4. Add, and I get a remainder of 1. Okay, so ignore the remainder. This would be your constant term, and this is your x term. So your slant asymptote would be y equals x minus 1. So what this function will approach. My y-intercept would be 0, -3/4 when I plug it in. When I plug 0 in, my x-intercept comes from my numerator equal to 0. So to algebraically get that, I would need to do the quadratic formula because that is not going to factor. So I just cranked out the quadratic formula. You can certainly use your technology to find the zeros of your function as well. So as a decimal, that's like 0.80, and it crosses also at -3.80. So almost -4, so really close to that asymptote. And really close to the slant asymptote as well. So if you actually graph this on your graphing calculator, you're going to see how much it hugs these asymptotes. Pretty amazing. Okay, so it doesn't ever get completely vertical. This even looks like it's turning around and going to the right, but it continually and infinitely approaches that vertical asymptote. Gets infinitely closer, but never ever touches it. Lastly, I am still missing the domain of the function, which would be -∞ to -4, where my vertical asymptote is, and then -4 to infinity.